Good morning, everyone. Welcome to Math Monday. I'm Miss Barnes, and the segment that follows is Math for kindergarten through second graders. Hi, friends. How are you doing this morning? I'm doing all right. Today, we are going to be working on thinking addition to solve a subtraction problem. So our objective today is I can use addition to solve a subtraction problem. The tools that we'll be using today are a part whole map and connecting cubes. I have those tools digitally. If you don't have cubes at home, you can use blocks or some of your toys or even pieces of cereal from your cabinet sometimes. So please make sure that you take a moment, get your part whole map ready, and find a tool that can help you count and solve these problems. And let's get ready to learn. All right, so like I said, our objective today is I can use addition to solve a subtraction problem. Let's jump right into the first one. Remember that when we're presented with a word problem, one of the most important things we can do is read the question from start to finish. So we really need to read it from the very first word to the very last punctuation mark. So let's read this one together. Sully needs 8 tickets to get on the ride at the carnival. He has 2 tickets now. How many more tickets does he need for the ride? Do you remember what the next step is in our process of understanding word problems? The next step is we need to write a sentence that will answer our question. So our sentence should say something like, Sully needs some more tickets to get on the ride. Okay. So that's going to be our answer statement. And we leave the blank there so that we know we have something to solve. Okay. Now the next step in our process is for us to go back, stopping at each punctuation mark and figuring out how to model that problem, part of the problem. So that's what we'll do here. The first thing is we'll go back and we will read sentence by sentence. So starting with the first sentence, Sully needs 8 tickets to get on the ride at the carnival. And there's a period, so we're going to stop there. Whoops. Drew on top of my word. Let's try again. I still kind of did, but we all know that's an H. All right, so we need to think about what this sentence means in the context of our problem. Sully needs 8 tickets. So we know that in a number sentence, there are at least 3 numbers. In our case, there will be 3 numbers. We'll have 2 add-ins and a sum, or we will have 3 numbers that we put into a subtraction problem. We also know that subtraction problems start with the total number of objects that we have. Does 8 reflect the total number of objects that we have? Sully doesn't have 8, but that's how many he should have if he wants to get on the ride. So that number does represent the amount of tickets that he will need in order to get on the ride. So we're going to model that in our part whole map by writing 8 at the top in the total box. My total box is really small, so my 8 doesn't fit into it, and that's okay. Let's read the next sentence. The next sentence says, he has 2 tickets now. And there's a period, so we'll stop. Tell me, how do I model the 2 tickets that Sully has right now? Well, that's pretty easy on a part whole map. I'm going to take the connecting cubes and we'll just drop 2 on the left side of our part whole map. Now that represents Sully having 2 tickets right now. How many tickets does he need in order to get on the ride? Well, we don't know, so we're going to put a question mark in this side of the part whole map. You'll see that there's space for a subtraction sentence right below the part whole map. We're going to come back to that later. So remember I said our strategy today is to think addition in order to subtract. So I am seeing this part whole map, and I bet you can tell me what an addition sentence with a missing addend would look like. Remember, the addends are the parts of the addition sentence that are being added together. So let's think about an addition sentence that we can write in order to solve this problem. Looking at my part whole map, I see that on the left side I have 2. And I know that with a part whole map I'm going to add the 2 boxes together, but I don't know how many is here yet. So I'm just going to put that line like we did in our sentence. That way we can solve for it in a little bit. And we know that 2 plus something equals the 8 tickets that Sully needs to get on the ride. So what do we do next? Well, next we need to solve this number sentence. So 2 plus what equals 8? There are a couple ways that we can talk about doing this. I'm actually going to create a more friendly number, and I'm going to break this unknown addend into 2 parts. So I know that 2 plus 3 equals 5, and that something else plus 5 equals 8. So the parts of the missing addend are 3 and something else. Well, now I can see that 5 plus something else equals 8. Well, how do we get from 5 to 8? That's right, we add 3. So 5 plus 3 equals 8, which means if we go back up, 2 plus 3 plus 3 equals 8. And now we have to talk about this part in the middle. So what is this here in the middle? What does that equal? 3 plus 3 equals, well, that's right, great job. 3 plus 3 equals 6. So we know that 2 plus 6 equals 8. Now I'd like to draw your attention back to that subtraction sentence over here underneath the part whole map. So now we're going to talk about how to take this addition sentence and turn it into a subtraction sentence with an answer. Then we'll complete our problem. So looking at the part whole map, can you see the relationship between the 3 boxes and their positions in the subtraction sentence? Let's try. What comes first? I already gave you this answer, so hopefully you were listening. Tell me what comes first in the subtraction sentence. That's correct, the total. So we're going to put 8 here because that's how many tickets Sully needs in order to get into the ride at the carnival. Then we need to subtract the part that we know he has. So going back to the problem, how many tickets does Sully have? That's right, Sully has 2 tickets. So we've already solved this subtraction sentence by creating our addition on the right side of your screen. So we know that 8 minus 2 equals 6. And that Sully needs 6 more tickets to get on the ride. Great job. Take a quick break and a deep breath, and we're going to get started on problem number 2. All right, problem number 2 looks a lot like the first problem that we did, except we're talking about my friend Rhea and her time at the beach. So let's start by reading the problem from start to finish. Rhea has 6 balls at the beach. A strong gust of wind takes 4 balls from her. How many balls does Rhea still have? So I'm going to go back and we're just going to read that again, stopping so that we can model. So Rhea has 6 balls at the beach, and we're going to stop there. What number does 6 represent? Does it represent a part, or does it represent the whole? Good job. So we're going to put 6 at the top of our part whole map. And again, I know mine doesn't fit, but I bet you got yours too. The next sentence says, a strong gust of wind takes 4 balls from her. So over here, we are going to model that the wind took 4 balls. So 1, 2, 3, 4. And we have to calculate how many balls Rhea still has. Okay, great job. So our subtraction sentence, when we are ready to solve it, remember where the pieces of the table go. Our subtraction problem will look like this. 6 minus 4 equals what? Now you already may know the answer to that, and that's great. But in case you don't, we're going to flip the problem and think addition in order to solve this subtraction. Remember, we can use our model here, our part whole map, or you can use the fact that you know makes 6. So we have to think 4 plus what equals 6. Well, let's break this missing number into parts. I know that 4 plus 1 equals 5, and that's pretty close to 6. So this is 5 plus something equals 6. And I know that 5 plus 1 equals 6, which also means that 4 plus 1 equals 6. And I know that this piece in the middle, 1 plus 1, I know that that equals 2. So 4 plus 2 equals 6. So going back to our subtraction problem was 6 minus 4 equals, and now we know that that equals 2. Great job. I've got one more problem to show you today, but we don't have time to solve it. So let me clear my drawings, and I'll just leave it here on the screen for you. I had such a great time working with you today. I hope you keep working this week, and I hope you enjoy the beautiful fall weather outside. It was my pleasure having you in class today, and I'll see you next week.
Kindergarten is great at Kansas City Public Schools.
I know they have really good teachers. I know this is a great school.
They teach them stuff that I thought my kids would never be able to know at the age of 5.
Since deciding to send our kiddos to a neighborhood school, we've become even more of a part of our community.
Now is the time to enroll your future kindergartner for the new school year. Visit enrollkc.org today.
The desire to create lives within each of us. From Grammy-winning producers and musicians, to NBA stars, to Navy admirals and Medal of Honor recipients, to internationally renowned artists and beloved local muralists, Paseo graduates have been creating their own success, their own history, their own legacy since 1926. Now it's your time. Create your future at Paseo Academy of Fine and Performing Arts. Learn more at enrollkc.org/Paseo.
KCPS students, I'm so glad you joined me again for Math Monday. Last week we talked about perimeter, and today we're going to review perimeter but also talk about area. Come on and join me and let's take a look at some problems.
Okay, let's review perimeter. Let's take a look at this first blue rectangle. Remember from last week, the perimeter is the total distance around an object, or the sum of all of its sides. Let's take a look at this first problem. I can tell from the information given to me that this rectangle has a total perimeter of 66 inches. That means the total distance around this rectangle is going to be what? 66 inches. Very good. I only know one of the side lengths, 8 inches. But because it's a rectangle, I know that if this side is 8 inches, then so is the corresponding side. This is also 8 inches. So together, 8 plus 8 equals 16. I know that of the 66 inches, these two sides make up 16 of those. Take a minute to think what I should do next. If you are thinking subtraction, that is right. So I'm going to take my 66 total inches and I'm going to subtract what I already know, 16 inches. 6 minus 6 is 0 and 6 minus 1 is 5. That means I have 50 more inches. The sum of these two sides is going to equal 50 inches. Now, if this side equals 8 inches, and so does this side, that means that these two sides are going to be the same amount. What two numbers can I double to get 50? If you don't know, I'll give you a hint. It's the same value as a quarter. If I double a quarter, what do I get? 50 cents, that's right. So that means that I can split 50 into two groups of 25. 25 here and 25 here. Have I found the missing side length? Yes, I have. Now, let's double check just to be sure. If the total perimeter is 66 inches, then that means all of these sides equal 66. Very good. So let's check. 25 plus 25 equals 50. Very good. 50 plus 8 inches equals 58 inches. 58 inches plus another 8 inches equals 66 inches. Excellent. So the answer to the missing side length of this problem is 25 inches. N equals 25 inches. Pat yourselves on the back. That was really good. All right, now let's take a look at the second rectangle. This rectangle has a slightly different shape. It gives us a perimeter of 32 centimeters. So that means that the total distance around this rectangle is 32 centimeters. Now, I'm going to give you a hint. The length of this side is 4 centimeters. So if this side is 4 centimeters, what do I also know? I know the corresponding side. So I have 4 centimeters and 4 centimeters. That gives me a total of 8 centimeters. If the total perimeter is 32 centimeters, I can do the same thing I did in the other problem. 32 minus 8 equals 24 centimeters left. So that means that the sum of these two sides must equal what? That's right, 24 centimeters. So take a second to think. What number can I double that will equal 24. Excellent! 12. I know that I can split 24 into two groups of 12. So that means that these side lengths must be 12 centimeters and 12 centimeters. Now, mathematicians always take their time to check their answer. So while I'm really confident that we got the right answer, I want to take a second to check. I know that the perimeter is 32 centimeters. That means the sum of all these sides must add up to be 32. Let's add them up. 12 plus 4 is 16. 12 plus 4 is also 16. 16 plus 16 equals 32 centimeters. Great job. Now let's talk about area. Area is the amount of square units it takes to cover a figure. Look at the figure I just drew. Can you see the square units in there? Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The area of this figure equals 20 units. It takes 20 of these individual units to cover the figure I drew. Remember, when you're finding perimeter, we're talking about the distance around an object. But when we're finding the area, we are talking about the amount of units it takes to cover this entire object. So let's take a look at the purple figure here. I know that this is a square, which means all of these sides are going to be equal. 22 yards is the measure of one side, and I know that that's going to be the measure of every other side since it is a square. If area is the amount of units needed to cover the figure, I'm going to be finding out how many square yards are needed to are needed to cover this square. I can do that by multiplying the length times the width. So I can multiply 22 by 22 because that is the length and the width. I'm going to give you a second to figure that out. The area of this square figure equals 484 yards squared. You can also write that as square yards. So this shape here has an area of 484 yards squared. So that means that there are 484 tiny square yards covering this entire figure. Now let's take a look at this next shape. This one may be slightly easy for you to multiply. It gives us the area. It says the area is 60 square feet. And we're also given one of the dimensions. We are given the width. So if the area is 60 square feet, and I know that area equals length times width, that means 6 times a number is going to get me 60. What times 6 equals 60? That's right, 10. 6 times 10 equals 60. So that means the length of this figure, the length of this side is equal to 10 feet. And I can check that by multiplying the length times the width. 10 times 6 equals 60. Very good. And that checks out with my area. We have time for one more problem. So let's put what we know about perimeter and area together. Let's take a look. A rectangle has a length of 9 millimeters and an area of 270 square millimeters. What is the width and what is the perimeter? Okay, so let's take a look at what we know. We know that the area is 270. And we also know that the length of this figure is 9 millimeters. If the formula for area equals length times width, I know that 9 times W is going to get me 270. Therefore, I can take 270 and divide it by 9 to get W. Or I can think about multiples. You choose which way you want to find W, and I'm going to give you a minute to think it out. All right, what did you come up with? W equals 80 millimeters. Very good. 9 times 80 equals 270 square millimeters. So the width is 80 millimeters. But we have another question. What is the perimeter? So if I know that W is 80 millimeters, I also know that the corresponding side is going to be equal. And I can also fill in the length of this side, which I know to be 9. What do I have to do to find the perimeter again? That's right, I got to add it all up. So 80 plus 9 equals 89. And the same over here, 80 plus 9 equals 89. I'm going to come down to some open space and add up 89 plus 89 to get my perimeter. 9 plus 9 is 18. 8 plus 8 is 16 plus 1 is 17. The perimeter of this object is 178 millimeters. Excellent job today, guys.
Thank you so much for joining me on Math Monday. I hope you learned a lot, and I'll see you next week.
My name is Mary Jo Fender, and this is Math for Middle School. Today we're going to go over how to compute the constant proportionality between quantities using values in a table. What you'll need today is paper and pencil to follow along. Okay, take a quick second and let's get ready to learn. Before we really talk about constant proportionality, we need to understand what is a proportional relationship. And two quantities are in a proportional relationship when the two quantities vary and yet have a constant ratio between them. So what we're going to be looking for today is that constant ratio. And that constant ratio is called our constant of proportionality. Our first example that we're going to use today is cooking. It's probably one that you're most familiar with because we all double, triple, and sometimes quadruple a recipe. At my house, we always like to make oatmeal cookies, and they never seem to go far enough. So our original recipe calls for 2 cups of oats to 3 cups of flour. Because we always run out seemingly sooner than we really want, we're going to double the recipe. And when we say double, that gives us our constant ratio right there because we're doubling it. We're multiplying times 2. So if you'll notice, our 3 cups of flour, when we multiply times 2, is going to be 6 cups of flour. Our 2 cups of oats, when we multiply times that same ratio times 2, is going to be 4. So our doubled recipe needs 4 cups of oats and 6 cups of flour. Remember, our constant ratio is 2 because we doubled. Another example that you guys might be familiar with is when you play soccer. And I have a table demonstrating soccer goals to attempts. Now you'll notice for every 1 soccer goal, they make 5 attempts. Now when we're looking for a ratio, we're looking for the rate of change between our x value and our y value. And when you have a table and it's going vertically, x is always on the left, y is always on the right. Now when we do that, we always want to say our y value to our x value. So we're going to look for shots to goals. Now our change in y from 5 to 10, that's a change of 5. 10 to 15, that's also a change of 5. On the goals, 1 to 2, that's a change of 1. From 2 to 3, that's a change of 1. So I'm pretty confident with our first 3 rows that our constant ratio is going to be 5 to 1. For every 5 attempts, we make 1 goal. So if we look at our 4th row of our table, it says we make 4 goals, but our attempts are left blank. How would we figure that out if we know 5 shots for every goal? So probably the easiest way you're going to do this is you're going to multiply that 4 times 5 to equal our shots attempted. Now we can go ahead and check this to make sure that our constant rate of change is the same. So the difference between 15 and 20 is 5, and our difference between 3 and 4 is 1. So we still have our constant ratio. Now you'll notice that our 5th row is left blank. We have our shots attempted, but we don't have our goals made. As in our 4th example, we multiplied times 5 to fill in our y value or our shots. We're going to reverse the process. So instead of multiplying times 5, we're going to divide by 5. So if I made 25 shots, that means I'm going to make 5 goals. Now I can go ahead and check by continuing to see my rate of change throughout my table. So the change between 20 and 25 is 5. The change between 4 and 5 is 1. So I know my missing information, I'll go ahead and circle it, that I filled in is accurate because I have my constant ratio. So let's talk about what is the constant of proportionality. Constant proportionality is the ratio that the two quantities share. So let's take a look at an example. So Charity can read 15 pages in her chapter book in 40 minutes. The table shows the number of pages she reads in 15, 30, and 45. We need to figure out what is our constant of proportionality, or what is the ratio that our two quantities share. So remember, we're going to look at our rate of change between our x value and our y value. And remember, the left side of the table is our x, the right side of our table is our y. Now, it really doesn't matter which vertical column you compare first, as long as they all have the same rate of change. So I'm going to go ahead and do my x value first. So the difference between 15 and 30 is 15. Our difference between 30 and 45 is also 15. Our difference between 40 and 80 is 40. And our difference between 80 and 120 is 40. So what is our ratio? So remember, it's always y to x. So our ratio is going to be 40 to 15. Now, can we simplify this? Absolutely. And we really need to take it down as far as we can go. Sometimes we can take it down to unit rate, or sometimes we can get it close. It all depends on what you're really looking for as your answer. Now, I know 40 and 15 can both be divided by 5. So 40 divided by 5 is 8, and 15 divided by 5 is 3. So what is our constant of proportionality? Our constant of proportionality is 8 to 3. Now, we also might want to write it as a fraction. And when we do write that as a fraction, we're going to put our y value on top as our numerator and our x value down below as our denominator. Now, these particular positions actually tell us something about our situation. Remember, our x value is the number of minutes, and our y value is the number of pages. So we can actually start putting labels on these. So I can say 8 minutes, and our 3 is going to be pages. So I can actually say Charity can read 8 pages in 3 minutes. So our constant of proportionality is 8/3, or 8 to 3. We have time for 2 more examples. So which situation is proportional? In this particular situation, we have hot air balloons and we have song downloads. We can use an equation, k equals y over x, or y divided by x, to figure out our ratio. Now remember, our vertical tables, our x value is on the left, our y value is on the right. So I'll go ahead and put those for both tables. Now we're going to use ordered pairs. And ordered pairs are going to be found on the same row as each other. And I've circled them for you. So let's go ahead and use our equation for constant proportionality and see what we find. So in the first ordered pair, 10 divided by 1, our constant of proportionality this time is going to be 10 first. I'm going to keep it in fraction form. I like improper fractions so I don't have to keep flipping back and forth. So our next constant, a proportionality equation, is 15 seconds. 15 seconds, 2 is prime, so unless 2 can go into 15 evenly, we can't simplify. It doesn't, so that's as far as we can go. Our third ordered pair is 20 over 3, or 20 divided by 3. 3 is also prime, so unless we can divide 20 by 3 evenly, it's already simplified. We can't. And the same, let's do 25 divided by 4 over 4. Only factors of 4 are 2. 25 does not have 2 as a factor, so that is simplified as well. You'll notice that each of these constants or ratios are different. So this particular table is not proportional. So let's take a look at song downloads. We're going to go ahead and use our ordered pairs. Remember, they're on the same row, 1x, 1y. And let's go ahead and use our equation. So I'm going to say 12 over 4, or 12 fourths. 12 can be divided by 4, so that's 3 over 1. Our second ordered pair is 24 eighths. Both 24 and 8 can be divided by 8. And again, that's 3 firsts, or 3 over 1. 36 twelfths. Both can be divided by 12, so again, that's 3 over 1. And then our final is 48 sixteenths. Both can be divided by 16, so that's 3 over 1. You'll notice that each of these constant proportionality is 3 over 1, or 3 firsts, or 3. So this particular table is going to be proportional. That concludes our lesson for today, so let's take a quick review before we end. So proportionality means two quantities share a common ratio. Constant proportionality is what that ratio is called. And we have an equation for constant proportionality, which is K is equal to Y over X. Thank you for joining me today, and remember to work on your proportions this week so you can continue to improve. It's been my pleasure having you in class today. I'm Mary Jo Fender, and I'll see you next week.
Southeast because of the culture, the band program, and restorative justice.
I love Southeast because of the academics, sports, and students.
I love Southeast because of the people, the energy, and the advanced classes.
It's not alike. I love Southeast because the students here at Southeast are full of potential and they believe in achieving anything.
We are Southeast.
Southeast.
We stand shoulder to shoulder.
Join the Southeast family. Enroll today.
I chose manual because it's challenging and fun, and it can help me with college.
I chose manual because I wanted to get a jump start in my career with culinary arts.
I chose manual to acquire skills I'd use in real life.
I chose manual because I want to be an ER doctor, and being an EMT is my first step.
Kickstart your future today at Manual Career and Technical Center. Manual is open for all 11th and 12th grade students in both Kansas and Missouri. Learn more today at enrollkc.org/manual or call 816-418-5200.
Hello, my name is Marcelina Lirius and welcome to Math Monday. In this video, we're going to describe the effects of parameter changes on graphs of quadratic functions. Before we start, I want you to get ready with your pen, your notebook, and if you have a graphing calculator, that would be helpful. So what happens if, given the parent function y is equal to x squared, in this case, the coefficient of x is equal to 1, so that's the value of a, which is 1. So what happens if the value of a changes or also if the sign of A changes. Then we will also describe the effect when H and K changes. So starting with the parent function y is equal to x squared, a here is equal to 1. A is the coefficient of the quadratic term. So when a is positive, the parabola faces upward. Okay? So this is now we're describing the orientation. And when a is negative, the parabola faces downward. So that's the effect of changing the sign of a. Now what happens if we change the value of a? So the transformation from y equals x squared to y equals ax squared when a is, okay, when a is equal to 1, we have the graph here where the vertex is at the origin and the parabola is facing upwards. So if the value of a is positive and greater than 1, okay, when the value of a is positive and greater than 1, how does this graph compare to the graph of the parent function here? Okay, so the effect of a is on the width or the opening of the parabola. So as we change a from 1 to 3, okay, a here is equal to 3, the graph narrows, okay? And if our a on this graph here, on the graph here, is a number between 0 and 1, so it's a fraction, or you can have a decimal between 0 and 1, notice the effect on the opening of the parabola. So the parabola becomes wider, okay? So to summarize, the value of a has the effect is on the width of the opening of the parabola. The bigger the value of a, in terms of absolute value, the narrower it is, and the smaller it becomes, the wider the opening of the parabola is. I'll pause to give you time to process and take down notes. Again, the effect of the value of a is the width of the parabola, and the sign of a is whether the parabola is facing upward if it's positive and facing downward if the value is negative. Next, let's look at the transformation of the parabola when our k now is not equal to 0. So this is our parent function, y equals x squared, a is 1, and we transform this into y is equal to x squared plus or minus k. If you have your graphing calculator, graph y is equal to x squared, and check if you arrive at this same graph. It's facing upwards because a here is 1 and it's positive. Now what happens if we add a value k, plus or minus k? Let's start first with the graph here on top, okay? So our parent function y equals x squared is the red graph, okay? That's the red graph here. And we have here added plus 3, okay? We added plus 3. So the value of k here, when you look at this blue graph here, or the purple graph, this graph is the original graph moved k units up, 1, 2, 3. So each point on the vertex is moved, each point on the graph will be moved 3 units up. So the k here displaces or moves the graph k units up or down. So it's a vertical shift. In the same way, when we have the graph here, when we have the function y is equal to x squared minus 5, the graph of this function as it relates to the parent function or the parent graph, which is the red graph here or the red parabola. So notice the translation, you have x squared minus 5. So which means that all points on this red graph will be moved 5 units down. 5 units down. So the green parabola is now the graph of y equals x squared minus 5. So take note, if the value of k is changed, plus or minus, okay, any value, then the effect is a vertical shift. Okay, plus k means k units up, minus k means k units down. Okay, take down notes and process the information. So the effect of k here is the vertical shift. Either k, if it's plus k, it's up. If it's minus k, it's down. Okay. Write this down on your notebook. Okay. Now what happens if we change the value of h? So in this case, we will consider again the parent function, and let's only look at the change on the parameter h. Okay. Y equals x squared is graphed on the side. It's a parabola facing upwards. Then let's start with the value when h is 3. So when h here is 3. If you solve for x here, h becomes 3, and that's the value of h. When you're looking at x minus h, you solve for h, you have x is equal to h. That's why h here is equal to 3. So look at the red graph. Okay, the red graph is y is equal to x squared. When we change this now to x minus 3, the quantity squared, the graph is shifted 3 units to the right. So h equals 3 means 3 units to the right. Okay, 3 units to the right. Be careful because this is a common misconception, because when students sometimes think because it's x minus 3, they have to move to the left. That is not the case. You have to solve for h here. H is equal to 3. Now let's compare to the graph of the function when h is negative. Okay, so if we solve for h here, when you have x plus h here, you actually solve for the value here of, okay, h here is negative 4. So h negative 4 means you move 1, 2, 3, 4. So the vertex here is moved 4 units to the left. Be careful. Again, the main confusion here, when students see the plus sign, they think that they have to move to the right. They have to move to the right. It's not the case. You have to move to the left. And the effect now of the transformation or the value of h is a movement from left to right. So this is a horizontal shift. Horizontal shift. Okay. Unlike the value of k, when it's positive k, move up, negative k down. In this case, when you have h is positive, okay, when you have an x minus h, it's actually a movement to the right, and movement to the left if it's x minus k. Copy? Okay. So now let's look at the transformation on these two graphs here. Let's start with the first one. From the parent function y is equal to x squared. And earlier we know that this is a graph whose vertex is at the origin. And if we start looking at the vertical shift or horizontal, let's start with horizontal. How many points did we move to the right? Okay, so 1, 2, 3. So this is a horizontal shift to the right, move to the right. And from here, we moved 1, 2, 3, 4. So it's 4 units up. Okay, 3 units to the right, 4 units up. Again, the up movement here or the vertical shift is denoted by +4. And the movement to the right is actually an x minus h, which is an x minus 3. So if we write the equation of the parabola, it's actually this: y equals the quantity x minus 3 squared plus 4. Then I'll give the second parabola here for you to analyze for your practice. And that concludes our lesson for today. And I hope to see you next week.